underway. Um, okay, so we are going to get cracking. We've got some poll questions that we have today, but today I'm going to continue with the um, kind of freebie, just because we're still kind of in a test or a piloting phase, I guess I would say. Just to make sure everyone's got their system set up. Because I know that last week, whenever we had a poll question, there was at least one person who said mine's not working. So I want to make sure that we have all those kind of hiccups squared away. But what we're going to be talking about today is I'm not sure how to check, but can you tell me if I'm on my TX state Zoom? Um, okay, so I got a private message from somebody. Last week I mentioned in an email or an announcement that you would need to sign in through your Texas State Zoom. Um, and I wanted you to try that today, but starting on Thursday. So I'm happy that this is brought up. Starting on Thursday, if you are not in your authenticated Texas State account, then you will not be able to join. So you'll just follow the link that I sent you that, it was basically go to txstate.zoom.com, I think, or zoom.t. No, I think it's txstate.zoom.com. Um, and log in through that. And so to answer this person's question, I'm not sure if I'm logged in or not. I believe one way that you would be able to tell is what you show up as in your like in the chat. For instance, I show up as Joel Gray. Um, if I was on my Gmail, then I think I might show up as just Joel or Joel Gray or my email at gmail.com. So if you followed that link, chances are that you did it properly. Um, but on Thursday, you'll know because you will not be able to join the meeting. And you know what? I could have kind of a test run maybe tomorrow during office hours. I'll just email everybody and say, hey, this is a time when you can test to make sure that you are on your authenticated account. Then if you encounter an issue, then just email me and I'll say, hey, well, I'll try to help you troubleshoot it. But in the meantime, I'm going to go ahead and share my screen. Um, so a couple of announcements. Thursday, you'll have to be in your authenticated account. Follow that link that I sent out. On Thursday as well, that's when your first quiz will go up and your first homework assignment will be posted. Then the last item is Zoom polls. We're still kind of piloting them, making sure that everyone's got the system set up. So if you're on a mobile device, you know how it appears so that you can actually respond to the question. Today I've got 5 questions on the agenda, so we'll try to make it through all those. Now, just a little bit of a review. Last week, well, one of the big things that we were talking about was we were discussing physical versus chemical changes and physical and chemical properties. And one of the things that we talked about was we talked about kind of clues or words that you could use that would be good, like reminders or triggers for, well, what is a chemical property? And some of the good ones would be like something burns, or if something ferments, or, an odor is produced. Those are good indicators of a chemical change. Now, these are 2 examples. Well, are these physical or are these chemical changes? Here, what we have is a Hershey's bar or a square from a Hershey's bar. And then over on this side, it's melted. Now, to me, it's kind of tempting to be like, oh, well, that is clearly a chemical change because it looks so different. But I would try to find something that you're familiar with, like an ice cube. Okay, can an ice cube take this shape? Absolutely. And if you allow that ice cube to melt and just heat it up, well, can it ultimately look like this? 100%. So this right here, on the left-hand side would be a good example of a physical change. On the right-hand side, we've got an Oreo and an Oreo that has been broken into several pieces. That is also a physical change because although the macro or on the large scale to the naked eye, the thing broke, um, we're not really having to break any bonds to like make this a different thing. And in addition to that, one thing that I always think about is we use these key words like burns, ferments, or, an odor is produced. Those are our clues of a chemical change taking place. Um, I've had plenty of Oreos in my life, and not once has, whenever I've broken an Oreo in two or taken the wafer off of the cream filling, have I ever smelled it and been like, this smells different. So I would use these terms, burns, ferments, odor, as qualifiers to identify something that has a chemical change, but also disqualifiers and say, okay, well, you know, this didn't ferment in order to get this way. So I'm willing to say that that is not a chemical change. Now, changing gears a little bit, what we're going to be looking at today is units of measurement. Now, there is a international governing body, um, IUPAC. This right here, the IUPAC is what it's commonly known as. This is, I believe, International Union of Physics and Chemistry, I believe. Um, and so this organization is kind of I don't know if I would say, yeah, I guess the governing body for important things for chemistry and physics. And so anytime that we talk about like um, standards, well, IUPAC kind of sets those standards. So, whenever chemists talk about, or if could anybody add to the chat a letter if you ever heard of a mole? Great. A number if you have not, obviously, or not obviously, but with our trend that we've been working on. So a mole is an amount of a substance. And that's what chemists use. Chemists, biologists, biochemists, physicists, they'll talk about quantities of substances and they'll say, oh, well, 4 moles of, let's say, kerosene. Add a number to the chat if you've ever heard of kerosene. Okay, great. 4 moles of kerosene were burned to ignite blah. Okay, so a chemist or a physicist will say that in this quantity right here is significant to them. That not the number specifically, but the unit, moles. Um, when we talk about chemical reactions, we're going to be talking about moles. And IUPAC is kind of the organization, I guess you could say, that is responsible for finding that common understanding. Now, some of these other units, for instance, meter, a length of something, will use a meter, and that's kind of your metric system compared to a foot or an inch, which is a part of the imperial system, the measurement system. So there's lots of overlap between the metric system and what IUPAC uses. Now, it doesn't capture everything because there are some things that are outside of that metric measurement system. But the units of measurement for mass are grams, volume, liters, time is in seconds, and then temperature is the only one that's a little bit tricky because it has 2 different units. Degrees Celsius and Kelvin. Now, an important thing to know is Um, could everyone add a Y or an N to the chat if they've ever heard of Celsius? Okay, so at least one person said no. Um, Celsius is not the drink, but instead it is, in this case, a temperature measurement. Like most of the time, if you go to the doctor and you get your temperature checked, or if you do it at home, it's going to be measured in degrees Fahrenheit. If degrees Celsius is a part of the metric measurement system. Chemists, oh, somebody added a G. A B? Oh my gosh. Neither of those are Y or N. Okay. But when we talk about Kelvin, that's temperature measured according to chemists. And the important thing about this is an absolute scale. Scale, not sale. Could anyone add to the chat a Y or an N if they understand what an absolute scale is? And if you have the time, could you give a brief description? You can send it to me as a direct message. What does that mean? What does an absolute scale mean? And there's a Nicholas, you're absolutely right. There's never a negative value. So what that means is that the Kelvin, like if you were to, let's say that you traveled right now to Antarctica. If you went to Antarctica right now, Arctica, I think that's properly spelled, it might be like negative 47 degrees Fahrenheit. And you look at that on the Celsius scale, and I don't know what that conversion is, but let's say that it's negative 32 degrees Celsius. Again, I don't know if that conversion is right. Um, this is going to be something like 240 Kelvin. And no matter how cold something gets, it is never going to go below zero. So zero is the lowest temperature. And so if you've ever heard of something or if you've ever like taken a physics class, maybe you've heard of absolute zero, that kind of that phrase. That just means that um, things are observed at that particular temperature or kind of hypothesized because that's actually something that's not really attainable or hasn't yet been attained. It's kind of a theoretical. So you might think, oh, well, if I go to, 500 feet below the surface of the ice in, or the below the surface in Antarctica, well, it's not going to be below 0 Kelvin. That's physically impossible. Okay, so I want you to know these units. We're going to be revisiting them. And, you know, I think that it's helpful to look around and find something that's kind of relatable regarding these. Um, for instance, I like Dr. Pepper, so I always think about volume and I think about, well, can I buy a 1 liter Dr. Pepper at the 7-Eleven? Absolutely. Can I visualize that 1 liter? Is it this big or is it this big? Well, it's about this big. Okay. Then when it comes to gram, okay, well, gram, that's kind of a distant sketch or a distant, that's a little bit of a stretch. But if I look around my desk, for instance, I've got nutritional or dietary supplements, and I'll look at that bottle and it says, oh, okay, well, this capsule has 1 gram of this substance. Um, Length, okay, a meter, that's a little bit of a stretch, but I know that I am just under 2 meters tall. Um, so I would think about this almost like 1 yard. Or if you ever, ran a track event in high school, or if you've ever run a track event or participated in a swimming event or something like that, maybe you can, uh, not just swimming, there's any number of events. Try to think about something that's like tangible to you. Seconds and degrees Celsius, well, time, I think that a second is pretty relatable. We're going to get more into moles as the semester progresses. I'm going to introduce it to you now, but we're going to dig deeper into it later on. Right now, what I want you to know with respect to moles is whenever somebody talks about 1 mole of something, typically they're talking about, um, well, they're using a mole as kind of like a filler. And what I mean by that is, and actually, could anyone add to the chat? If I tell you that I have 1 dozen eggs, how many eggs do I have? Got 12. So if I tell you that I have 2 dozen eggs, got 24 eggs. If I have zero point 0.5 eggs, got 6. Perfect. Those are the things that are relatable. You know what those are, and you know that 1 dozen of something is 12 of that thing. So if I tell you I have 1 dozen dollar bills, I have 12 dollar bills. If I tell you that I have 1 dozen bicycles, I have 12 bicycles. If I have zero point 0.4 moles of bicycle, or sorry, zero point 0.4 dozen, no, let's say zero point 0.5 dozen bicycles. Oh, I have 6 bicycles. These are things that you understand and you know. Now, that, so 1 dozen is a definition. Now, that is the same thing that I want you to use whenever you're looking at this. So 1 dozen equals 12. Well, 1 mole is this many. 6.02 times 10 to the 23rd. You're absolutely right. Can I put eggs in terms of moles? Yeah. If I have 1 mole of eggs, and I always like to write this out just to kind of send the point home, then I have 602,000,000,000,000,000,000,000. I got to make sure I'm writing enough zeros. 2, 1, 2, 3, 4, 5, 6. If I have 1 mole of eggs, I have 602,000,000,000,000,000,000,000,000,000,000,000,000 eggs. Does that make sense? Give me a Y or N to the chat. Okay. So 1 mole is a definition. Now, to me, I always struggled with this because this is such a bizarrely large number that it didn't make sense to me. And so to avoid writing out, what is this, like 21 zeros? What we use is something known as scientific notation. This is based on powers of 10. So we take this number right here and we rewrite it as 6.02 times 10 to the 23rd power. Okay, so 1 mole of eggs is the same as 602 times, or 6.02 times 10 to the 23rd eggs. Now, what makes this, so what I want you guys to think about with respect to this is, how do we come up with this number? This number right here is written in what we will refer to as full notation. And what I want you to do, what skill I want you guys to be able to do, is to be able to convert a number from full notation to scientific. and I want you to be able to convert a number from scientific notation to full notation. Now, I'm going to go ahead and take a pause on discussion of moles because we're going to revisit that and we'll get more into it. For the time being, what I want you to know about this is I don't want you to get boggled down into how large that number is, but what I want you to do is I want you to look at this and answer this question for me. Is this a positive or a negative exponent? And you can answer with the symbol. Add it to the chat. Okay. You're absolutely right. It's not a dollar sign. It's a positive exponent. Now, what I want you to do is think about this as answer this for me. Is this number, and this isn't a trick question, is this number larger than 1? Y or N to the chat. Great. This number is absolutely larger than 1. So what I want you to do is I want you to think if you're given a number in full notation that is larger than 1, use a positive exponent. And I'm saying that because that's in comparison to using a negative exponent. So let's go ahead and let's take the number 5,000. Now, this is going to have a positive exponent when we take this full notation and we convert this number to scientific notation. But the fair question is, or a fair question is, okay, how am I going to write this? Well, let's go ahead and write 5.0 times 10. Or, yeah, we'll go with that. 5 times 10, we know that it's going to be a positive exponent. And if we were to kind of visualize where the decimal place is, it's right here. Because we know that this number is 5,000. Okay. Terry, you're absolutely right. It's times 10 to the third. How did we determine that? Well, we placed this decimal and then we said 1, 2, 3. 5 times or 5.0 times 10 to the third. This could also be written as 5 times 10 to the third. Now, I want to go ahead and erase this. I want to give you another number. 530. Write that in scientific notation or using scientific notation and add it to the chat. Oh, I've got some good answers there. 5.3 times 10 to the second. Yeah, we've got 5.3 times 10. We know it's a positive exponent. We imagine that our decimal is right here, 1, 2. Yeah. So we move the decimal place 2 spots. Okay. Can we add a Y or N to the chat if, yeah, I follow that. I'm good. And an N if you're like, I need some more examples. Okay. Seeing lots of yeses. We're going to do some more examples. Okay. So Y and N. I didn't mean for it to be, yeah, we're moving on. We'll never do this again. Right now, we've looked at positive exponents. A positive exponent is where your number is larger than 1. Now, I want to contrast that to this right here, 0.001. 0.053. I'm not looking for answers, but I would like you to answer with a Y if this number right here is larger than 1, and an N if this number is smaller than 1. 0.053. Spot on. It is smaller than 1. Now, that is significant because what that means is that, well, this statement right here doesn't really work for us for 0.053. So we've got to change this statement. The number is smaller than 1, so we're going to use a negative exponent when we're converting from full notation to scientific notation. Now, before we do that, though, I'm going to give you a poll question, the first of our poll questions for today. Which one of these numbers, and let's go ahead and because we haven't really talked about it yet, we're going to scribble this one out. Which one of these is the largest? So please don't answer D. Answer A, B, or C. Do not answer D. We'll be doing some more polls. If you're on the mobile device, you might have to tap your screen and then it will kind of flip it around. How do I go back to the question? I'm not exactly sure how to answer that because I don't really know your setup. I've got the poll still active, so I'm not really sure why folks are going away. I'm not trying to be belligerent and be like, I can't help you, but I don't really know enough about your setup right now to help you out. Okay, I'm going to go ahead and stop here. And I'm going to have more poll questions. And keep in mind, when the poll pops up, it takes over the whole screen, so we can't see the question. Whenever you tap your screen, does it bring it back? Okay. Um, hmm. Well, let me look into that, and I'll post an announcement a little bit later today. It's in more. Then press poll/quizzes. I tapped, I screened it. Okay. So it's in the more, press poll/quizzes, and that should bring it up. So let's test that out whenever we do our next poll question. But for the meantime, in the meantime, let's go ahead and answer this. Our question is, which number is the largest? We've got B and C, which are in full notation. It popped up over the question for me, but if you're on a computer, you can drag the window over. Okay. Um, we've got these two numbers, 240 and 24,000, which are in complete notation. We are looking for the largest. For mine, I got another question, so I answered wrong. The question was the look on the screen was the text, and that's what the next one is going to be. So this is why I like to do kind of the troubleshooting. So for the first few days when we do the polls, everyone kind of gets them, we can figure it out. Okay, so 24,000, is that larger than 240? It is. So B is out. 11 folks answered B is the correct answer. We're really down to A versus C. We've got 24,000 versus 2.4 times 10 to the third. Okay, this is kind of, I'm asking you to reverse engineer what we did. What we've been doing is to take the number and convert it from full notation to scientific notation. This one has us going from scientific to full. Well, we've got a positive exponent. So what we're going to do is we're going to move going from scientific to full notation. So we want to get rid of the decimal. 2.4. So we've got to move it 1, 2, and 3. So can you add a Y or N to the chat if you deduced what this to this was? Okay, awesome. And in the event that you didn't, now we've got that. So we ultimately ended up with 2,400 versus 240 versus 24,000. Okay, so just for practice, let's go ahead and write this number. Well, actually, you know what we can do is we can look at all of these numbers in scientific notation. 2.4 times 10 to the third. Taking this number, and sorry, I'll write my exponents a little smaller. 240, write that in scientific notation. 1, 2. We're leading with 2.4 times 10. We move the decimal 2 places. Then this last one, 1, 2, 3, 4. You're absolutely right. Kanan and Ryan, 2.4 times 10 to the fourth. So what we arrive at here is we've got comparisons of our exponents. So if I gave you a different question that was, I'm going to stop the share of this question or the results there. If we had 2.9 times 10 to the first, 2.9 times 10 to the 15th, 2.9 times 10 to the 23rd, A, B, or C. Well, if you saw this on a quiz or a test, you would know C is the correct answer. The largest exponent, the largest positive exponent, gives us the largest number. Okay, now this last question or this last answer option, I erased it because I didn't want anyone to use it because we hadn't really talked about it. We've got a negative exponent. What I want you guys to think about is when you have a negative exponent, and I want to go over this because our next poll question is going to be dealing with smaller numbers. So we've got a negative exponent. Whenever you see that, I want you to think the number is smaller than 1. Okay. So in this case, let's say I had 2.4 and I was like, okay, well, I'm kind of in a jam. I need to convert this number from scientific notation to complete notation. How would I do that? Well, which way can our decimal go? It can go right or it could go left. Now, if I move my decimal to the right, the smallest number I'm looking at whenever I move that decimal to the right is 24. Add a y or an n. Is that number, is 24 larger than 1 or is it smaller than 1? Y for larger and n for smaller. Great. Okay. So we know based on that, we're not going to be moving our decimal to the right. Instead, what we need to do is we need to move it to the left. How many spaces are we going to move it? 1, 2, 3. I did see somebody previously added this, but our number ends up being 0.0024. We moved it 3 spaces to the left. Now, let's go ahead and do another practice question. Okay, so actually, could you give me a 1 in the chat to communicate this to this makes sense, or a 2 if, wait, I don't follow that at all. Okay. Okay. So now let's go ahead. I want to give two other questions. We're going to go from full notation to scientific notation, and then scientific notation to full notation. Full notation, if you had the number 0.0001, 5, we'll do that. the first question, if you, I think that it's helpful to kind of have like if you've ever heard of computational thinking, like what is a computer going to do if it's confronted with this number converting from full notation, six, to scientific notation? Well, the computer is going to ask the question, is this number larger or smaller than one? Well, it's smaller than one. So by it being smaller than one, I want to go ahead and start writing my answer out as times 10 to the negative, because this number is smaller than one. Now, the next question is, okay, well, what am I going to end up with? What is my answer going to have? My answer is going to include all of the non-zero digits in this number. 1 and 5 are the only non-zero digits in this number. So I'm going to write 1 and 5. Now, the pattern when writing a number in scientific notation is to write one digit right here with a decimal, and then any other digits, any other non-zero digits, or any other relevant digits. So I've got 1.5. So the standard, or whenever you're writing a number in scientific notation, it's always one digit followed by any other important digits to include. Now, if I had, yeah, so if this was, actually, I'm not going to go there. I'm just going to go with, okay, so I know exactly where I need to move my decimal. I need to move it between the 1 and the 5. So I'm going to say 1, 2, 3, 4. So I've moved it 4 spaces. So I'm going to go with 1.5 times 10 to the negative fourth. Okay, now we've got a number. I'm going to go with, let's see, 1.0394. Sure. So how can I explain how I got 1.5? Think about scientific notation as looking at a number and asking how many non-zero digits does it have? So 1 in this case, 1 and 5 are the only numbers in this number that are not 0. So what I'm going to do is I'm going to put one digit followed by a decimal followed by another digit. So the X here is that first digit, that 1. This next X is the next digit. So I've got 1.5 times 10 to the negative fourth. Now, in this other number, 1.0394 times 10 to the negative, let's say, sixth. Now, to address Julia's question here, how did I get 1.5? I get 1.5 the same way that this is 1.0394. Where I'm going with that is if you saw this number, 103.94, that would not be in scientific notation because the decimal place right here needs to be between the 1 and the 0. So it's digit followed by, or let me rephrase that. There is going to be one digit to the left of the decimal and then however many other ones to the right of the decimal. Okay, does that make sense, everyone? Actually, add the number of digits that will be to the left of a decimal whenever you write a number in scientific notation. And add that to the chat. Perfect. Great job, everyone. And then, however many are to the right, it just depends, number by number. So in this case, we've got 1.0394 times 10 to the negative sixth. In which direction am I going to be moving my decimal when I convert this to full notation? L or R to the chat? Perfect. Left. Absolutely right. Or absolutely correct. Sorry about that. So whenever I take this number and convert it to full notation, I'm going 1 2, 3, 4, 5, 6. So I think that you're right there, Victor. 0.12345 10394. Okay. Great job, everyone. Now let's apply that. Write this number in scientific notation. Yeah, it's 1.23 times 10 to the negative fifth. Now what I want to do is let's tackle this next poll question. Which number is the smallest? We've got 2.4 times 10 to the third, 0.024, 0.00024, and 2.4 times 10 to the negative third. And I'll just go ahead and act along with you guys. I'm going to convert this. I'm going to standardize all my answers. And I'm going to say, okay, positive exponent. It's just, to me, it's more practice, or it's beneficial practice. Well, I'm moving this 3 spaces to the right. 1, 2, 3. So 2, 4, 0, 0. Then answer option D. Well, I'm moving it to the left since it's a negative exponent. 1, 2, 3. So 0.0024. 85% of the class chimed in with C. That's the correct answer. Now it's 82%. This is a good time for going ahead and practicing to see if you're able to toggle back and forth between poll question and no poll. I'm going to go ahead and, 89 folks answered, and we have 110. I'm going to go ahead and end this poll though. Again, this is we're still doing the practice. Okay, so just a second. 85% ended up answering this correctly. And again, we'll have another poll question, or we'll have some more poll questions in just a moment. So, why is that? Okay. Um, so, and as I said previously, and it's been a minute since I said this, I am not going to be grading or assessing based on accuracy of your answers. I'm looking for, did you participate in this poll or not? So don't stress about, oh, I picked the wrong one. I'll talk about them all, but that's about it. Now, let's see. Okay. Sorry, just a second, everyone. Um, okay, so next up, we've got when we're dealing with these very small numbers and very large numbers for that matter, we have prefixes. And I want to go ahead and jump ahead to this. We have what are known as the metric prefixes. Some of these are maybe a little bit familiar to you, others may not be. Now, with that in mind, I've got a bottle of Nature's Bounty Selenium. Some people will pronounce it selenium, but I bring this up because this is something that there's a little bit of an error here. If you look at this bottle, and I think that it's, yeah, selenium. If you look closely, it says the quantity, 200 mcg. Now, this bottle, each one of these pills has 200 mcg. This is micrograms. Now, if you look at this list of metric prefixes, where I want to draw your attention is to this column right here, prefixes. Some of these might be familiar to you, others may not. tera, giga, mega, kilo, hecto, deca, deci, centi, milli, micro, nano, pico, femto. I want you guys to be able to know from mega to micro and to be able to kind of convert freely between those. These all have different symbols. If you looked at that bottle that I showed you, it said MCG. Well, that's different from this right here. That's a microgram. That is the Greek symbol mu, and that is how this bottle should read. It should say this. But chances are, if you go and you put that on a bottle, people are going to be like, I don't know what the heck that is, but I have no interest in buying that. Now, what I think is the most helpful thing to do is to think about this and try to find something that you're familiar with. Again, this is tricky, but your base unit is right here. Could anyone add a number to the chat if they have ever or if they watched the TV show Breaking Bad? Okay, so lots of folks have watched Breaking Bad, and um, I watched like 7 episodes, I think. Then I had to call it. It was too much, too violent for me. But one of the things that people kind of find memorable about that show is the quantity. Not necessarily like, oh, I was really excited to watch about quantity. No, instead, whenever they talked about moving drugs, they were always talking about kilograms. So, kilograms, or kg as it would be. Not KD, Kevin Durant, but instead kg, kilograms. So if your base unit is 1 gram, if you're going up, that is larger than one, or that's multiple of it. If you're going down, oh, Kevin Garnett, thank you very much. That came as a private message, but yes, KG, Kevin Garnett. If you're going down, well, then the unit is smaller than that base unit. So what I'm getting at is if I were to take one of these selenium pills, well, it's 200 micrograms. Is that more or less than 1 gram? M for more, L for less. Yeah, it's less than 1 gram. 200 micrograms. So I'm talking about right here. Now, that to me is very helpful to put these things into perspective. Like I said, there's a range that I want you guys to know about, from micro all the way to mega. Some of these prefixes you might be a little bit familiar with. Centi, like a centimeter. Well, there are 100 cm in 1 meter. So this 0.00 or 0.01, that is 1 centimeter compared to 1 meter. Should we download this formula? I think that I mean, I would be comfortable with these conversions. Um, what I would recommend is I would recommend working my way up. So again, give yourself kind of statements about each one of these. I have 1 gram of sugar. That's my base statement. My follow-up statement would be if I have 10 grams of sugar, I have 1 DA or decagram of sugar. Then after that, if I have 100 grams of sugar. I have 100 H, so 100 grams of sugar, 100 of the base unit, hecto or Hg of sugar. I would recommend doing that. So then you can kind of put these things into the proper context. Yes, it would be. Oh, you're right. I'm so sorry about that, Kelly. You're absolutely right. It would be 1 Hg. Thank you very much for clarifying or for correcting me there. And then if I have 1,000 grams, it's equal to 1 kg. 1 million grams is equal to 1 capital mg. Okay, now to go the opposite direction, well, I always like to think about it as how many centimeters or centigrams, cg, are needed for 1 gram. Well, then what you can do is say 1 divided by 0.01. That's going to tell you that it is 100. Okay. Now, these prefixes, they being able to do this sort of or answer these sorts of questions will be basically a comparison. Kind of similar to these numbers, but it will be familiarize yourself with these numbers and the sequence of them. And then you'll be able to say, yes, this is more than this. Now, there are some instances where we have a repetitive letter. For instance, lowercase g is reserved for gram. Capital G is reserved for giga. So G is 1 gigagram. Again, you guys don't have to know all the way up to giga. Mega is the highest that you guys are being asked for. Then kg versus, that's a lowercase k versus Kelvin, capital K. Your capital K, you're not going to use that for grams. So there's no such thing as a Kelvin gram or anything like that. M for milli is the same as the lowercase m that's used for meter. Capital M for mega is, well, when you have a million of something. Now, to apply that, when we measure the mass of something, what is the mass of this apple in scientific notation? Well, notice how this number right here, 172.3, is that in scientific notation? It's not, because 172.3 is not, well, it is not the proper organization for a number in scientific notation. It needs to be 1.723. Now, in terms of kilograms, well, that would be 0.1723 because 172, and this would be 0.1723 kilograms. Now, measuring volume, so the space that something occupies. Scribble these out for just a second. Okay. This is a milliliter. Is a milliliter larger or smaller than a liter? L for larger, M for smaller. Wonderful. Smaller. You're absolutely right. When we look at this, this is known as a graduated cylinder. This is going to be in milliliters. 50 is at the top. right here where our solution comes up to is at 45.0. So 45.0 milliliters. Now, there are 1,000 milliliters that make up 1 liter. What you can do is you can say, all right, well, 45, the measurement that we have, 45.0, and then divide that by 1,000 milliliters. So we're relating all these to liters, and that would be 0.0450 liters. Okay. Now, there are other conversions. So I do want you to know that 1 inch is 2.54 centimeters. So the length of this pencil in centimeters is 17. So from 0 all the way to 17.35. 17.35 centimeters. And this is 6.831 inches in inches. Time measurements. These are conversions that you're probably pretty familiar with, and I do want you to be able to do. How many seconds are in 6.5 minutes? Well, 1 minute has 60 seconds. Well, 6.5 times 60 equals 390. We talked about, let's see, yeah, this is, okay, cool. We talked about temperature and we talked about the absolute scale. I do want you to know that Kelvin is an absolute scale. So it goes as low as 0 and no lower. Degrees Celsius, on the other hand, well, it doesn't. Degrees Celsius, it can be negative 35 degrees Celsius. Now, in order to convert from Celsius to Kelvin, all that you do is you take the temperature in degrees Celsius and you add to that 273. Sometimes you'll see it written as 273.15, but add 273 to it. So if it's 55 degrees Celsius out, add 273 and you get 328 Kelvin. Okay. Now, the last thing that I'm going to talk about today, because we've covered a lot of stuff, is to compare the different temperature scales. So we've got temperature in Fahrenheit, Celsius, and Kelvin. What I think is most important is to look at the lowest numbers. Starting over with Kelvin. The lowest temperature possible is 0. The lowest temperature possible for Celsius is negative 273. And before anyone says, oh, but what about negative 274 degrees Celsius? This is a place where I am going to be discouraging. And I'm going to say, no, that's physically impossible. That cannot happen. That would bend the space-time continuum. Not sure if that's a proper phrase, but it cannot be lower than that. So negative 273, that's it. Same thing goes with the Fahrenheit scale. Negative 460. Well, can't be negative 461 degrees Fahrenheit. Oh, but what about in some sort of magic lab? Well, in a magic lab, that's a different thing. But what about in a controlled lab situation? Nope, it cannot. Cannot be negative 461. Negative 460 is it. Negative 273 is it. But most importantly, and the point that I want you to know is this 0 right here. I want you to be able to convert from Kelvin to Celsius and Celsius to Kelvin. So if there are two really important points from today's lecture that I want you to, skills that I want you to take away, I want you to be able to, and I'm going to go back to this right here. Take a number from full notation to scientific notation and take a number from scientific notation to full notation. If you're thinking to yourself, like, what are the three most important things from this class? I think it's helpful to narrow it down that much. The most important thing is this skill right here, being able to go from full notation to scientific notation. The second most important skill would be able to go from degrees Celsius to Kelvin and from Kelvin to degrees Celsius. And the third most important is to be able to convert between these numbers. So taking that information, if you're like, okay, well, how do I use that? Well, one way is you could use this information that I just shared with you as, okay, I'm going to use my studying. I'm going to base my studying on that. I'm going to write or find 10 questions. Well, I would recommend that probably six of them are scientific notation to full notation and back and forth. Then I'd find like two questions or maybe three questions that were about Kelvin to degrees Celsius, and then maybe one question that's about this. Just kind of coming up with comparisons. Okay, folks, that's what I've got. That's our stopping point for today. Tomorrow, what we're going, or not tomorrow, on Thursday, we're going to talk about density. We've already kind of talked about it, which is why I'm not too worried about going over it kind of briefly or quickly. Not briefly, we're going to be sacrificing anything, but it's just going to go a little bit more quickly than today. Um, we did, I ended up having two poll questions because my polling function was a little bit funky. Um, Again, today was just kind of more trial. So everyone's getting credit for the poll questions today. I'll post one last poll question. There's not actually a question here. So you can just I'll leave it up for a little while for you to play around with and toggle back and forth. The question's live now. It says on screen A, B, C, or D. There's not a right or wrong answer for this. There's not credit or no credit. This is just, can you toggle back and forth between, oh, I want to see the screen. Now I want to look at my question. That's what the purpose of this is. I'm going to go ahead and stop my recording and I will post this a little bit later today.